this video, we're going to look at some more applications of the gradient vector. So this problem is actually a continuation of another problem that I did previously where I used this temperature function and I found the rate of change of temperature with respect to distance when an object moved from the point 1, 2, 3 in a couple different directions. We use this for some directional derivative examples. Alright, but here we've got the same temperature function that we had before, the same point that we had before, but we're asked something slightly different here. We're asked what direction should we go from a particular point so that temperature increases as rapidly as possible with respect to distance, and what is the instantaneous increase in temperature as we leave that particular point. Alright, so these are both just direct applications of the gradient vector. The direction that we go for maximum function increase would be the gradient of the function evaluated at that point, and then the magnitude of that gradient vector evaluated at that point gives me the instantaneous rate of change in that direction. So there's not a lot of work to this problem, it's just a matter of recognizing what you need to do to get the answers. Alright, in the previous video we calculated the gradient vector, so I'll just go ahead and write that down here. And we also evaluated the gradient vector at the point 1, 2, 3. Okay, so if I want to know the direction in which we should go from this point so that temperature increases as rapidly as possible, we should go in the direction of this gradient vector. So we could just give our answer as that, in the direction of that vector. Any positive scalar multiple of that vector will also work. So for example, I could multiply through by e to the 8th and divide through by 20 and get a simpler version of a vector that is in the same direction as this vector. We want to make sure that we keep a positive scalar multiple of this vector so that we don't change it to an opposite direction. So this vector, -2, -4, -1 would work, or if you prefer to give your direction as a unit vector, you could do that as well. So any of those would work for the direction of the vector. Be sure if you're doing online homework, you're paying attention to what it's asking you to enter for your answer, how it wants you to give that answer. And then for the second part here about what is the instantaneous rate of change of temperature as we leave that point, that would be the magnitude of our gradient vector. I shouldn't use one of these other ones because I need the magnitude of the full gradient vector. Okay, so when I find the magnitude of that gradient vector, I get the square root of 8,400 times e to the -16, or if I want to simplify that, I can write that as 20 e to the -8 times square root of 21. If I want a decimal approximation, I believe you get about 0.031, and that would be in degrees Celsius. That's our units on temperature per whatever the units on x, y, and z are, and it tells us in the problem that those are in meters. Alright, so this is our maximum rate of change of temperature from that point. Alright, do some problems with some applications of the gradient.